Hey everyone, the objectives of this video are A with respect to B. So if we do that on the vector diagram, that would be, this is the position of A, so this will be our origin. We'll have a rigid body in here. So this is our origin, we'll define that as our origin. This point here is A. This point here will be defined as B. So, and this point here will define as R of A with respect to B. So we'll put an arrow in here. It should be like so, such that when we do vector addition, this R of B is here, and this R of A with respect to B represents this vector in here. So we end up getting this vector R of A. Okay, for convenience sake, the motion of the translating point with respect to the stationary point is considered to be the motion of the translating point. So the notation becomes what we've got up here, or what we've got just here. Alright, relative motion defines general plane motion completely, as well as the motion of a point on the rigid body with respect to another point on the same rigid body. It may also describe the motion of one rigid body or any point on that body relative to another rigid body or point on the second rigid body. So if we do the time rate of change of this, like we did in our previous video, we'll end up with the velocity of A is equal to the velocity of B plus the velocity of A with respect to B, where velocity just represents any change in the position. So if this vector here, if we have another, I'll do another diagram in here. If we have an origin here, and we still have the same position vectors, the same kind of rigid body shape. It's a bit different, but it's a general shape, okay? And this body wants to translate across to here and then rotate like so about point B dash. So we'll label this B dash. So this is where B has gone from its initial position. This is A dash, so where A has gone from its initial position, and the body is then to rotate about this fixed position once it gets to here, and we'll end up with a point at A double dash. So if we have a rigid body in here, the change in relative position, so V of A with respect to B would be the change in this relative position here in a vector direction that has not changed until we get this rotational part. So the rotational part represents the relative position change. So if this was our body, we'd get the rigid body facing like so. So it would translate to here and then rotate like so. But that would be in general plane motion. So it's a combination of translation and rotation, like we were talking about in the initial introduction video. Okay. Another thing we can also look at is an instantaneous center of zero velocity, but we're going to do that in the next video. Like I said, relative motion may be broken down into components like translation and rotation by using vectors that define both the translational motion, which is this term in here, and the rotational motion, so the relative velocity of one position with respect to another position. So, or so 1 point with respect to another point, sorry. So this point here with respect to this point, that has an angular velocity like so, but this has got no angular velocity, so that's where this term comes from. If there was no rotation, it would be the same, and the body would just translate. Okay, so the reason that the relative velocity is always denoted as so is because pure rotational motion, we use a fixed axis about which the rotation occurs, and in pure translational motion, we consider the linear motion of a body, but in general plane motion, we must consider both at the same time, which can only be done by superimposing the translation and rotation. Alright, that's all I'm going to do in this video. Acceleration is much the same. So I'll write down the acceleration equation here. So acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B. Now we'll notice that this term in here has tangential and normal components, so we'll write that down, plus A of A with respect to B normal plus A of A with respect to B tangential. Now all that really means is that if we have a rotational motion occurring here of a rigid body, so this is the path it's following, it's going clockwise like so, we have this rigid body, there's going to be a tangent at this point in time, so when the body gets to here, we'll go with this A and B, but we've changed the names, but it's arbitrary at the moment. This is our rigid body, so these are going to remain the same. This length here is going to remain the same. But if we're looking at the tangent and the normal components, so the tangential component of acceleration is just going to be perpendicular to this length here at any given time. So this is going to be our acceleration A with respect to B tangential, and our normal acceleration is always towards the point that it's rotating about. So our normal acceleration would be this in here, this whole thing here. So A of A with respect to B normal would be this in here. Okay, that's all I'm going to do in this video. The next video I will go over instantaneous center of zero velocity, and I might cover a little bit of motion relative to rotating axes where we have a change in the axis, so the axis is rotating as well as the body. Alright, thanks for watching.